Okay, that time we cared almost exclusively about global things. Now we're going to care almost exclusively about local things. Shapes of graphs. Okay, what we're really going to be talking about is what can we learn about a graph or a function from its first and second derivative. Okay. All right, we're human. Some of us are pretending to be. And so we try to understand the properties of functions and their behavior using graphs often, okay? We like to visualize things. And so far we've learned how to graph things that are transformations of functions we already know about, but sometimes we get unfamiliar functions, okay? So combining what we're going to learn today about what the derivatives tell us with things like asymptotes and symmetries and roots and domain, we can construct reasonably good sketches of unfamiliar functions. Okay, and we're only going to do an aspect of this today, and the rest will be in tutorial. So we're going to talk today about what derivatives tell us, and in tutorial we'll talk about how to sketch a complete graph. Hopefully. Oftentimes we just ask a computer to do this for us. Okay, so it's quite easy to just punch something into a computer and tell it to graph it. But the computer really is giving you sort of a discrete version of the graph. It's sort of coming up with a bunch of points, connecting them, and then you're hoping that that's an accurate representation. Okay. But to be convinced that you're not missing anything, so suppose you're not missing anything in the ends, or that if you zoom in you will find something surprising, to have exact values for various features, or to be able to identify patterns and trends in families of functions, you need to use your head. You need something like calculus. Okay, so today we'll be talking about what derivatives can tell us. What can derivatives of a function tell us about its graph? Okay, and in doing this we'll learn about features of functions in general, so even if you don't care about sketching, this is still useful. Okay, and the answer to what can derivatives tell us is almost everything, right? The only thing they can't tell us, as you'll find out later, is vertically where the graph is, but they tell us everything about the shape of the graph. Okay? Okay. Right, so we start with the first derivative. Okay, way back in lecture 1.1 when I decided that the chalkboard wasn't enough, we talked about what increasing, decreasing, and monotonic mean. Yeah? Okay, so on an interval, a function is increasing if going to the right takes you up, decreasing if going to the right takes you down, and on an interval, you're monotonic if you're either increasing on that interval or you're decreasing on that interval, okay, on the whole interval, okay? Again, this is overblown. If you think about what I said, or you can picture what increasing and decreasing mean, that should be good enough, okay? And again, you should have this from long ago. Okay, note that our definitions are strict, okay? So all those inequalities are strict. There's no equal signs anywhere. So for example, something like this, okay, we would not call that increasing on its domain, okay? Because there are places where going to the right doesn't take you up, you still stay at the same level, okay? So that's not strictly increasing, and so by our definition, it's not increasing, okay? Some people have a definition of increasing and decreasing that's weaker, okay? They replace those strict inequalities by weak inequalities, so greater than or equal to and less than or equal to, and they would call something like this increasing everywhere, okay? FYI. So you'll see that definition in places. And what that lets you do is you can call this thing increasing despite the fact it's got a prolonged flatness. Okay, but for us, this is not increasing everywhere. Okay, that's that. That is largely FYI. And again, don't fuss over crazy specifics of definitions, get a feeling for what we're talking about. Okay. Let's talk about the increasing, decreasing test. Which I'm thinking almost all of you know about. Okay, again, the big section here is first derivative, and this is the subheading of it. Okay, so what can the first derivative tell us? Okay, let's see if we can do this properly. Okay, there's a graph of something increasing. Let's look at some tangents. As you likely know, or can see, all the tangents have positive slope. Okay? And that is a general rule. So again, the point there is we have something increasing. Notice the tangents all have positive slope. And indeed, the sign of the derivative, which tells you what the slope of the tangent is, or the sign of the slope of the tangent, the sign of the derivative tells you if you're increasing or decreasing. Okay? If the derivative is positive over an interval, then f is increasing on that interval. If the derivative of f is negative over an interval, then f is decreasing on that interval. Okay, sign of derivative, you can just write that if you want. Okay, the sign of the derivative tells us, the sign of the derivative or the sign of the slope of the tangent tells us if f is increasing or decreasing. Positive increasing, negative decreasing. Fair? Okay. And if you want to prove this rigorously, use this thing called the mean value theorem, which we don't talk about, but you can ask me about if you want. Okay. Ad nauseum, one last time. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. And we can use that to come up with something else that we care about. The first derivative test. And these are all called tests to stress you out, obviously. Something like that happen? Okay, we use the derivative to tell us if we're increasing or decreasing. Now we use the derivative to tell us which critical points give us local extrema, local maxima or minima. Okay, we said last class we can only get local and indeed global extrema at endpoints and at critical points. But then we said not all critical points produce these extrema. Okay? So we're going to talk about which ones do. Okay, there we go. There's your rule. We're going to think about f being continuous, so nothing upsetting happens. Suppose that c is a critical number, a critical point of f, meaning the derivative of f is 0 or undefined at c. If the derivative changes from positive to negative as we go through c, then f is a local maximum at c. So what are we talking about? Okay, at c, let's say f and f prime. Okay, so if the derivative goes from positive to negative as we go through c, then the function goes from increasing to decreasing. Increasing to decreasing. And so look, we have a local maximum at c. Do another example under this. Okay, so if the first derivative goes from positive to negative as we go through C, the function goes from increasing to decreasing, and so we wind up with a local maximum at C. Okay, similarly for the minimum, just draw those things upside down, and you go from negative to positive in the derivative, so the function goes from decreasing to increasing, and you wind up with a local minimum at C. If you go through C and you stay positive, okay, so you go from increasing to increasing, or you go from decreasing to decreasing in the function, or the derivative goes from positive to positive, or from negative to negative, then you have no local extrema at C. Okay? Okay, so this is the local max case. You can draw the local min case. Again, not every critical point produces a local extrema. Okay, they're just candidates for local extrema. So, let's see, let's do some cases. So, we're talking about, even if f is continuous, then having a critical point doesn't guarantee a local extrema. So, in these two cases, the derivative at 0 is 0, okay? Flat, flat. Yet in this case, we wind up with a local extrema because the function goes from decreasing to increasing, or the derivative goes from negative to positive. But in this case, there's no local extremum at 0. The function goes from increasing to increasing again. Okay, or the derivative goes from positive to positive. Similarly, if the derivative is undefined, okay, that's not enough. You need to do the first derivative test to see if you've got a local extremum or not. In this case, we have a local extremum. We go from decreasing to increasing. The derivative goes from negative to positive, so we have a local minimum. But in this case, we just go from increasing to increasing, or the derivative goes from positive to positive, and so we don't have local extremum. Okay? So again, don't just check critical points. Look around them, apply the first derivative test, and see if they actually are local extrema or not. Okay? And that top case of not differentiability is a corner, and the bottom case is a vertical tangent. Does that make sense? Okay, critical point is not enough. You have to use the first derivative test. You have to look around the critical point. FYI, derivatives on intervals inside their domains, like continuous functions, have the intermediate value property. And so a derivative can only go from positive to negative or negative to positive through either a 0 or through a place where it doesn't exist. Okay? FYI. Okay, so again, a derivative can only change sign through a point where it's either 0 or non-existent. In other words, a critical point, which jives with what we've been talking about this whole time. Little special case, by our definition, closed endpoints are always going to give us local extrema. Okay? So, I'm going to call them closed endpoints. I don't know what the technical term is. At closed endpoints, by which I mean the endpoints of an interval that are included in the interval, you could check the derivative nearby, assuming things are sufficiently nice. Check the derivative nearby to see if it's a local max or a local min. So for example, suppose it's the left endpoint, and you're looking like that. If you're decreasing, what is that? It's a local max. It beats its neighbors. Beats or ties its neighbors. So it's a local max. That's F. F prime is negative. Okay, so again, by our definition, we get local maxima minima not just at critical points, but also at endpoints. So when you're looking at an endpoint, check the derivative nearby to see what the function's doing, okay? If you're at the left and you're going down, the derivative is negative, then you're going to wind up with a local max, okay? I won't write out the full rules for that. If you need them, let me know, but you can just figure that out each time, okay? Just think about what the derivative means, draw yourself a sketch, whatever. Okay, and another example, if you're at the right endpoint and you increase toward it, again, you've got a local max. Okay, that guy beats or ties its neighbors, and the derivative in this case is positive. Does that make sense? Okay. So the rule we talked about over there was really only for critical points. At endpoints, you can do a sort of pseudo first derivative test. Okay? Okay. Okay. Example. And again, in this, I'm assuming that we're continuous and nice and low. Okay. Find local extrema and intervals of increase and decrease of the function x squared times e to the minus x. I'm deciding if I should say that thing or not. So FYI, the derivative can only change sign through critical points. Okay. All right, we want to find the local extreme of this thing. Notice today we're not talking about global at all. Okay, what's our domain? Everywhere. This guy will take anything, this guy will take anything, their product will take anything. So the implied domain is the real line. Okay, if we'd given you a domain here, you'd be using that. Is the function continuous there, or do we have to worry about stuff? Yeah, it's continuous. That's continuous, that's continuous. The product's continuous. So f is continuous there. Okay, and that domain has no endpoints. So we've lucked out. Or lucked in, I can't tell. Okay, if there were endpoints, you'd also have to check for local max and min at the endpoints. Okay, but R has no endpoints, so we don't have to worry about that here. Again, don't forget, check the endpoints. Okay, there we go. And it's continuous, so life's going to be good. Excellent. Okay, so we need the first derivative. Okay, derivative first times second plus first times derivative of second. And we make this look nice by factoring. And if you want, you can write it like this. There we go. Okay? All right, so we did that y because we need to look at critical points for one thing, so let's find the critical points. Okay, where's f undefined? I'm sorry, where's the derivative undefined? Where's the derivative undefined? Nowhere, okay? This guy is differentiable everywhere. This guy exists everywhere, you're good. So the derivative is undefined nowhere. Again, whoa. Don't forget to check. Those count as critical points. Don't forget to check for the derivative not existing. Where's the derivative? 0. So where's this thing 0? Okay, what do we got? This guy's always going to be positive, okay? So it's either this guy's going to be 0 or this guy's going to be 0. So x equals 0 or 2. Okay, if you have trouble seeing that, let me know. Okay, so we got no endpoints in this case, and the only critical points are 0 and 2. Okay, we use our critical points to partition our interval. Okay, critical points, partition the interval. Or our domain. So let's look at what that means. Here are x values. Okay, the critical points were 0 and 2. There's no endpoints to think about. The critical points are 0 and 2. And now we need to see what our derivative does in each of these pieces in between. Okay? I don't care how you do this, okay? One thing you could do is you could just look at each of the factors here. We've got a minus sign there. This guy's always positive. If x is below 0, that guy's going to be negative, and that guy's going to be negative. You're going to have negative, positive, negative, negative, and that should give negative. So it'll be negative there. Between 0 and 2, that's still negative. That's still positive. That guy becomes positive. That guy's still negative. So we've got minus, plus, plus, minus. Multiply all those together and you get a plus. Past 2. That guy becomes positive. That guy's still positive. That guy's positive, and we wind up with minus. That's one way to do it. What could you do? You could list the factors here, okay? See what the sign of each factor is, then multiply those up and see what the answer should be. And if you don't know what I mean there, let me know. I think in the first tutorial we talked about this. Or what you could do is you could just pick a test number in here, so like -1, plug -1 into that, and then see what sign you get. Okay, for in here, plug 1 into it, see what sign you get, and for over here, let's say plug 3 into that expression and see what sign you get, okay? And by that expression, I mean this thing. Okay, see what sign you get, and just put those in there. Does that make sense? Okay? All right. So somehow or other, find out what sign the derivative takes on all those open subintervals. Okay, the derivative is negative, the function is decreasing. The derivative is positive, the function is increasing. The derivative is negative, the function is decreasing. Easy as that. Okay? Again, to find these signs, either look at the factors and think about what's going on, list them if it makes your life better, multiply them up at the bottom, for instance. And if you can't figure out what the signs are, you could use test values. Okay, so pick a number that's in this interval, evaluate the derivative there, pick something in here, evaluate the derivative there, and so on. Again, if you don't know what I'm talking about, let me know and I'll show you. Okay. And we're essentially done. Okay. F is increasing on 0 to 2. F is decreasing on -infinity to 0. And on 2 to infinity. Increasing on 0 to 2, decreasing on -infinity to 0, and on 2 to infinity. Okay? And so we have a local minimum. We have a local minimum here, okay? Okay, so just look at that and that should be obvious, or read the first derivative test over and over again. So we have a local minimum here at 0, and there, what's the value of the function? You plug into the expression for the function, 0 squared e to the minus 0, that's just 1, that's 0, so 0. And you have a local max, okay, where you go from increasing to decreasing, or the derivative goes from positive to negative, at 2. And there, the maximum value is, the local maximum value is 2 squared e to the minus 2, or 4 over e squared, or approximately 0.541. Again, if I'm saying anything that doesn't make sense, or too fast, or too confusing, just tell me. Okay? Alright, so what did we do? We found the critical points, we noticed there were no endpoints, the function was continuous so life was good, we found out the sign of the derivative on each of the subintervals that our critical points broke our interval up into. We checked if our function was increasing or decreasing on each of those subintervals, and we used that to decide if there was a local min or local max at each point. Okay? And that's it. Okay, and then we find the values of the local min and local max. And as always, there's a picture color-coded. It's decreasing where promised blue, it's increasing where promised orange, and there's our local min, there's our local max. Okay? And incidentally, that is a global min. That is not a global max, if this happens. You may remember from long ago, don't worry about this, because this thing's continuous, these increasing, decreasing intervals, I could have said 0 to 2, including 0 and 2, and I could have included 0, and I could have included 2, but don't worry about that. Okay? So just for the record, because this thing's continuous, I could have closed those intervals on which we're increasing and decreasing. If you want to know what I'm talking about, just ask me. But again, don't worry about that. Second derivative, unless there's questions. Again, don't confuse the derivative and the function. Okay, so for critical points, don't accidentally find the zeros of the function. When you're doing this, don't accidentally find the sign of the function. Okay, don't get the derivative and the function confused, and if I do, let me know. Okay, second derivative now. What can it tell us? Let's draw y equals x cubed. Okay, I'm going to be a maverick and not label the axes. What do we got? We got something like this. Okay? This thing is increasing everywhere. Okay? But it's going to bend differently on either side of the y-axis. Okay? So again, this thing is increasing everywhere, but it bends differently on either side of the axis. Okay? How do we describe something like that? So how do we describe how the curve bends or turns, sort of, or curves? Loosely speaking, how do we describe that? How do we describe how the rate of change is changing? The second derivative. How is the rate of change itself changing? Okay, the rate of change of the rate of change is the second derivative. Okay, so let's talk about this. Again, I'll color code it today. Okay, so the first thing we talk about is concavity. Okay, if the graph of the function lies above all of its tangents on an interval, then we say the graph or the function is concave up or upward on that interval. If the graph lies below the tangents, we say it's concave down or downward. Okay, a definition I don't recall ever using in calculus myself. You could probably get by without thinking about it. Okay, so what am I talking about? Let's draw some tangents here in distinguished white chalk. Tangents. Okay, over here, we're sitting below our tangents, okay? And if I said if we're below our tangents, then we're concave down. Concave down. Here we're sitting above all our tangents, so we're concave up. Concave up. Above the tangents, obviously, except at the point of tangency. Okay? So we sit below our tangents, we're concave down. Sit above our tangents, we're concave up. Okay? Or you could think what? Concave down means you're part of a frown. Concave up means you're part of a smile. Concave up means you open up. Concave down means you open down. What else we got? Let's say that's it. Does that make sense? Okay. It's what it sounds like. If you don't know what concave means, let me know. I recall at some point we were talking about how do we know if our linearization estimate was an over-approximation or an overestimate or an underestimate. And we said it matters if the tangent is above or below the curve. Hey look, above or below the curve. So concavity gives us that information. Okay, concavity tells us about whether we're getting an overestimate or an underestimate when we do a linearization approximation. All good? And again, I went through quite a lot of calculus, in fact all of it without ever using that definition. I just knew what concave up and down looked like. Okay, so this guy's concave up. Here's your function. Now let's see what's going on here. Let's draw some tangents. Let's pretend that touches. Okay, what's happening? As we go that way, the slope of the tangents is increasing. Slope of tangent increasing. That's the same as saying that the first derivative is increasing, because the slope of the tangent is just the first derivative. So the rate of change of the rate of change is positive. So the second derivative is positive. And it's just that nice, okay? Concave up, second derivative positive. Concave down. F, good. And in this case, the second derivative is negative. Okay? And that's what that second thing says, the concavity test. If the second derivative is positive on an interval, then the graph is concave up. If the second derivative is negative, then the graph of f is concave down. Okay? Okay, so the sign of the first derivative told us if we're increasing or decreasing. The sign of the second derivative tells us if the first derivative is increasing or decreasing, and therefore if f is concave up or concave down. Okay. We're about to stop. Okay, when f was continuous, and the first derivative changed from positive to negative or negative to positive, we saw that the function turned around and we wound up with a local max or a local min. Okay, now, where the function's continuous and the second derivative changes sign, we change from concave up to concave down, or concave down to concave up, and we wind up with what's called a point of inflection, a change of concavity. Okay, so if f is continuous, at c, And the sign of the second derivative flips, okay, positive to negative or negative to positive, and thus the concavity flips from up to down or down to up. As we go through C, then we have a point of inflection at C, okay? Again, second derivative is a derivative, okay? So it too has the intermediate value property, which you don't really need to know about, okay? What does that tell us? It tells us that this kind of thing, that the sign of the second derivative can only switch through where the second derivative is 0 or non-existent, okay? So where the first derivative has a critical point, in case you care. Okay, so if you're looking for where a sign might switch, you would look for where the second derivative is non-existent or 0. Okay, I'll stop with this warning. Here we go. Again, a warning, okay? Even if f is continuous, the second derivative being 0 undefined is not enough to give you an inflection point, okay? You have to look around, okay? So here the second derivative is 0 in these two cases, okay? But here we have an inflection point. We go from concave down to concave up. Here we don't. We're concave up everywhere. Okay, here the second derivative is undefined, okay? Vertical tangent and cusp. And in this case, we have an inflection point. We go from concave up to concave down. And in this case, we don't, because we're concave down here and we're concave down here. Okay? So it's not enough to check that the second derivative is 0 or non-existent. You have to look on either side and see if the concavity is actually changing. Is the second derivative sign actually changing? And that tells you if you've got an inflection point or not for a continuous function. Ladies and gentlemen, have a very pleasant weekend. Those of you who have a test again, good luck, and I'll see you on Monday. Okay, hello everybody. Last time we were talking about the shapes of graphs and what the first and second derivatives can tell us about the shapes of graphs. And yesterday I added that slide, so if you want to start writing, start writing. And if you want to take it off the web, take it off the web. I added that slide as an overview for the stuff we talked about. So we'll go over that now. Hopefully this helps you make sense of things if they don't already make sense. Okay, basically I'm talking about the role of the first derivative and the second derivative. The sign of the first derivative, plus or minus, tells you if the graph or the function is increasing or decreasing. Transitions between increasing and decreasing can only happen where the derivative becomes 0 or non-existent. And again, I mentioned a reason for that. And I said FYI. That fact is not FYI. You'll be using this a lot, okay? What is FYI is the reason for that, which is that derivatives have an intermediate value property. That you don't need to know, but this you should know, okay? So again, the sign of the first derivative tells you if the function is increasing or decreasing, and you can only transition from increasing to decreasing behavior or from decreasing to increasing behavior where the first derivative is 0 or undefined, and we call those what? The critical points of f. Okay, if f is continuous, and the sign of the first derivative flips, and you go from increasing to decreasing, or decreasing to increasing in f, then f has a local max or a local min. Okay, and again, local maxes and local mins can also happen at endpoints. As for the second derivative, its sign tells you if the graph of f is concave up or concave down. Transitions between those kinds of behavior, again, because of that intermediate value property you don't need to know about. Transitions between that kind of behavior, between being concave up and concave down, can only happen where the second derivative is 0 or non-existent. Okay? So if you want to look for candidates for where a function will go from increasing to decreasing or decreasing to increasing, you look for the critical points of f, okay, where the derivative is 0 or undefined. If you want to look for places where the concavity might change, you look for where the second derivative is 0 or non-existent. Okay? So this tells you candidates for switches in behavior. And again, if f is continuous and the sign of the second derivative flips, then you have an inflection point. Concavity has changed and the graph was continuous. And that's it. Any questions about this thing? Okay. Again, all stuff we saw before. And again, note, the first derivative being 0 undefined, in other words, where f has a critical point, that's not enough to get a local max or a local min. You need to check further, use the first derivative test or something, check further, and that was why I gave you that first warning slide. It said something like, don't forget. That first warning slide was about that. The second warning slide was about don't assume that if the second derivative is 0 or undefined, then you have an inflection point or a change in concavity. You might not. You need to check around. You need to check on both sides, see if there actually is a switch in concavity. Okay. Any questions? All right, we'll do an example. If you have a question, speak up. Here we go. We had a function last time, it's going to be the same function. Describe the concavity of the function x squared times e to the minus x, and identify the x-coordinates of all points of inflation. Okay. Okay, last time we talked about where this thing was increasing and decreasing and where it had its local extrema. Now we're going to talk about its concavity and its points of inflection. Okay, we already talked about how the implied domain of this thing was everything. I think we already said that the function is continuous on that domain. And we already found its first derivative. Okay, the first derivative was negative x e to the minus x, x minus 2. Okay? Okay, we need to find the second derivative. Okay, why do we need to find the second derivative? Because we're talking about concavity, and we're talking about points of inflection, and that's what the second derivative knows about. Okay, so we find the second derivative. I'm not going to go through finding this, okay? So I'll just write the result. If you have trouble getting the result, let me know, okay? You could use the sort of extended product rule here. You could expand this thing and go through it that way. Whatever you want to do, do it. And if you have trouble, just let me know and I'll show you. In the end, you get this as your second derivative. E to the minus x, make that bigger, times x squared minus 4x plus 2. We're looking for regions where the concavity is the same and places where it changes. So what did I say? When you're looking for candidates for transitions, what do? You look for where the second derivative is 0 or undefined. That's what I was talking about there. Okay, and those are the critical points of the first derivative. But that's a weird way of thinking about this. Okay, so let's see, what do I want to say? Look for potential, or possible, or candidate, concavity transition points. Okay, so see where the second derivative is undefined. Don't forget, where's the second derivative undefined? This guy looks pretty defined everywhere, okay? So that function is not only differentiable everywhere, it's twice differentiable everywhere. Okay, so the answer is nowhere. okay, or more importantly, nowhere on the domain, but the domain is R. Okay, so the second derivative is defined everywhere. Where is the second derivative 0? Which is the other possible place where you could have a change in concavity. So we need to see where this guy is equal to 0. This guy, you know about exponentials, this guy can never be 0. Okay, this guy's always positive. So it must be this guy that's 0. Okay, you can try factoring that all you want, unless you're happy to factor with irrational stuff, then you'll use the quadratic formula there. Okay, so you'll use the quadratic formula. Use quadratic formula. Okay, and you'll wind up with 2. Yep. Two minus root 2 or 2 plus root 2. Okay? All right. So, what are the candidates for transition points in the concavity of this thing? There's nothing to talk about there. And then we got those 2 points. Okay, so those are the possible transition points. Not confirmed yet, they're just candidates. Okay. Okay, so kind of like last time, except now with the second derivative. Let's see how this thing behaves. Okay, so we need to know the sign of the second derivative on each of those open subintervals. How do we do it? I like to think of this graphically. If you don't, use whatever way works for you. Okay, so that thing, okay, its graph is a parabola. It opens up, okay, this bit, right? Okay, this bit, its graph is a parabola. It opens up because that's positive. The leading coefficient is positive. And the x-intercepts are those 2 guys, okay? So, if you like to think of it that way, okay, what do we got? An upward opening parabola, and this is the graph of x squared minus 4x plus 2. Okay. And that's 2 minus root 2, that's 2 plus root 2. Okay, great. Now, that guy I said was positive everywhere. Okay? So the sign of the second derivative is given by the sign of this thing. Okay? Over here, the sign of that thing is positive. There we go, positive. Over here, the sign of the thing is negative. Negative. And over here, the sign is positive. Okay? That's how I like to think about it. You do whatever works for you. Okay? You like to talk about this kind of stuff algebraically, that's cool too. If you like to pick a test value in here and just see the sign of that, test value in here, see the sign of that, and test value in here and see the sign of that, that works too. Okay? Whatever you want. That works. Okay. Is that all right? Okay. Again, this was positive, so the sign of this was the sign of this, and I got the sign of this off of that picture. Okay. Second derivative tells me about concavity. If the second derivative is positive, then I'm concave up. Negative, concave down, positive, concave up. Okay, that's my shorthand for those things. If you write up and down, that's cool. Okay? It might just look like a piece of that. Okay, please say if you have a question. All right. spell out the answer to the question. What do we got? F, or the graph of F, is concave up on here. And on here. And it's concave down in the middle bit. Good. I just restated what's in the picture. Now we're looking for points of inflection. What's the requirement for a point of inflection? You change concavity and you're continuous. Okay, we said this thing was continuous everywhere. It changes concavity here, and it changes concavity here. Okay? Again, don't just check for the zeros or non-existence points of this thing and call those points of inflection. I hope I've been saying point of inflection. Don't just do that. Actually make sure that the concavity flips at those points and that the function's continuous. And then you have a point of inflection. Okay, so the last thing is F, or the graph of F, has points of inflection at, let's say, x equals 2 minus root 2, and x equals 2 plus root 2. Okay, because the function is continuous there, and the concavity flips. Okay, or the sign of the second derivative flips. Okay, and if you want the y coordinates, what do? You plug into the original function and you find the y coordinate. Questions about this? Okay. So you find candidate points of inflection, or sorry, you find candidate places where concavity could change. You check the concavity in the subintervals, and you plot points of inflection. Is that what I want to show? No. There's a picture. I'm coming back in. Okay. And there you go, proof by picture. Okay. Color coded, orange means concave up, blue means concave down, and those are your 2 points of inflection. Everything as promised. Okay, something that has points of inflection that we've seen before is this thing. Okay, these are the trajectories of the logistic growth model. Again, don't worry about specifics, I just want to show you a picture. Okay, I mentioned this, and I'll mention it again now. If your population starts below half of carrying capacity, you wind up with an inflection point when you hit half of carrying capacity. Okay, so this thing goes from concave up to concave down. Okay, you're initially your growth rate is initially increasing, and then your growth rate is decreasing. Okay, so if you start anywhere down here, you're going to wind up with an inflection point here, and that's where the population is growing most quickly. If you start at half of carrying capacity or above, you don't get the inflection point. So your fastest growth is right at the beginning. Okay? So that's it. As an example of an inflection point and what it could mean. And in this case, it means the maximum growth rate of the population. Okay. Second derivative test. Incidentally, there is a nice way of showing that that's where the inflection point could happen. If you want, just let me know. Okay. so we talked so far about, we talked about a lot of things, but one of the things we talked about was finding local minimum and maximum using first derivative test. Nice. I hope you all get well soon. Okay, we talked about the first derivative test to find local maxima and minima using the sign of the first derivative and continuity. But there's something called the second derivative test, okay? Sometimes, in some situations, the second derivative can inform us and tell us if we have a local max or a local min. Okay. And that's all it is, okay? So if the first derivative at a point is 0, so you have a stationary point, which is a special kind of critical point. If you have the first derivative being 0 at a point and the second derivative being negative, then you've got a local maximum. Okay? If you've got the derivative being 0 and the second derivative being positive, then you've got a local minimum. It's easy enough to see. Okay, let's say the first derivative is 0 and the second derivative is, which one's first? Negative. Okay, so what does that tell you? So we're concave down. Okay, so it's at C. Okay, so that's what this thing tells us, right? At C, we've got a horizontal tangent, thanks to this thing, horizontal tangent, and we're concave down because the second derivative is negative, looks like that. The tangent lies above the curve in that neighborhood. And so we've got a local max, okay, which is exactly what that says. You can just see that every time without having to write that out. Okay, local max. Okay, horizontal tangent, concave down, you get a local max. Okay, similarly for local min, you just get a picture that looks like that. Okay? Okay. Unlike the first derivative test, we don't have to look around the critical point anymore. Okay, we just look at the critical point. We get the first derivative at the critical point, we get the second derivative at the critical point, and that's enough. We don't have to look on either side. Okay? So you might think that's convenient. This test is useless where a second derivative test is useless if, or let's say it's useless at endpoints. Okay, where you can sort of use a version of the first derivative test to see if you've got a max or a min. It's useless where the first derivative is undefined, does not exist. Okay, so at critical points where the first derivative doesn't exist, this thing doesn't work. Okay, this thing only talks about where the first derivative is 0. And it also doesn't help you where the second derivative is 0 or does not exist. Okay? It only informs you if the first derivative is 0 and the second derivative is negative or positive. Okay? If one of those derivatives fails to exist, or if the second derivative is 0, then this thing's uninformative and you can't get any information out of it. Okay? So you can't say if there is a max or a min, you can't say anything. You have to use something else like the first derivative test. Okay? Also, in a lot of cases, finding the second derivative is a pain in the butt. Okay? So there's a lot of reasons why this test is annoying. Okay? But sometimes it's convenient. Okay. So for our example, x squared e to the minus x, we found that the first derivative was 0. This was last time. The first derivative was 0 at 0 and at 2. Unless I'm mistaken. Good. Okay, we found the first derivative was 0 at 0 and 2. Okay, so we can use the second derivative test to figure out if those points correspond to maxima or minima, or if the second derivative test can't tell us anything. Okay. We just found the second derivative of this function, so we can plug 0 and 2 into that to find this. second derivative at 0 is 2, which is positive. Okay, again, we found those two stationary points last time. We talked about the second derivative this time. You can either use the sign chart we made or just plug 0 into the expression for the second derivative to find out that that is positive. And since we have first derivative 0, second derivative positive, we wind up with a local min. Okay. And we can find that the second derivative at 2 is minus 2 over e squared, which is negative. Okay. First derivative 0, second derivative negative, tells you you've got a local max. Okay? And again, either plug 0 and 2 into the expression for the second derivative that we found, or use the sign chart, and if you have trouble with that method. Okay, and again, notice where the second derivative is positive, and the right conditions are met, you get a minimum, okay? So you might think those are opposite things, that if, you got a positive, then you wind up with a min. Okay? That's it for that one. If you've got any questions, let me know.